Last time we introduced the notion of Hölder continuity. Here's a reminder of what that is. If we have a path, and now let's stick to a compact time interval, the interval from 0 up to 1, taking values in some metric space S, and if alpha is some number in the open unit interval, then we say that path is Hölder continuous with parameter alpha if there's some constant k, depending on the path, so that the distance between the path at two different times is controlled by that constant times the distance between the times s and t to the power alpha. Now, in order to work with the constraints of countably additive measures, we're going to need to work with countable dense subsets of this time interval. Fortunately, Hölder continuity works well with countable dense subsets. And here is one demonstration of how. Suppose that D is any dense subset of the unit interval, and suppose that our metric space is actually complete. If we have a function omega defined only on D, that is alpha Hölder continuous, meaning that this property here holds for all s and t in D, then there exists a unique extension of that function omega to omega bar defined on the full unit interval that is also Hölder continuous with the parameter alpha and with the same Hölder constant k. The proof of this is nearly identical to the proof of the comparable statement where we just have continuity instead of Hölder continuity that we proved earlier in this course. Let's run through it one more time. We just need to define omega bar of t for each t. So we'll do that by selecting any sequence that we like, Tn, that converges to t. Since D is dense in the unit interval, there will be such a sequence. And we define omega bar, the extension, at that time t, to be the limit as n goes to infinity of omega of Tn. Of course, we need to check a number of things. Why does this limit even exist? And even if it does, why do we get the same answer no matter which sequence we choose here? Well, both of those follow from Hölder continuity here. The limit exists because if I measure the distance between omega of any two times in the sequence, by assumption, that's less than or equal to a constant, which depends only on omega, so it doesn't vary with n and m, times Tn minus Tm to the alpha. Now, alpha is greater than 0, and so since Tn goes to t, Tn is a Cauchy sequence, which means that this tends to 0, and so therefore does that. So this tends to 0 as n and m go to infinity. And we conclude from there that the sequence omega of Tn is a Cauchy sequence in S. But S is assumed to be a complete metric space, which means that that Cauchy sequence has a limit, which is what we're defining this to be. Great. But why do we get the same answer no matter which sequence Tn we choose here? Well, basically the same calculation again. If I have two sequences Tn and Sn, which both tend to t, then the distance between omega at those two sequences is less than or equal to the constant times Tn minus Sn to the alpha. And because those two sequences both tend to the same limit, that distance goes to 0. And that shows that these two things have the same limit. And so this is perfectly well defined. And finally, we need to see that omega bar is actually an extension of omega. Well, if t is any time in D, we can just take Tn to be the constant sequence t, 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 etc. And therefore, omega bar at t will be defined to be the limit as n goes to infinity of that sequence, which is just the constant omega of t, which is omega of t. Therefore, on D, omega bar and omega agree. And that shows that we have a well-defined extension here. The last point we need to show is that this extension, omega bar, is alpha Hölder continuous on the full interval 0 up to 1 with the same constant as the original function omega. And that also follows from a simple limiting argument. If I fix any two sequences, Tn going to t and Sn going to s for any two times, t and s in the unit interval, then the distance between the extension of omega at s and the extension of omega at t is, by definition, the distance between the limit as n goes to infinity of omega of Sn and the limit as n goes to infinity of omega of Tn, but this is just the limit of this vector in S cross S. And D is a continuous function on S cross S in the topology that it defines, of course. And so therefore that's the same as the limit as n goes to infinity of the distance between omega of Sn and omega of Tn. But once again, this is less than or equal to that constant times Sn minus Tn to the power alpha. And so that shows that this whole thing here is less than or equal to that constant times the lim sup as n goes to infinity of Sn minus Tn to the alpha. But that lim sup is actually a limit. Since Tn goes to T and Sn goes to S, this is equal to S minus T to the alpha. And that shows that indeed omega bar is alpha Holder continuous with constant no bigger than k of omega. But by definition, k of omega is less than or equal to k of omega bar because omega bar is an extension of omega. And so if the inequality here holds for all of omega bar, then it also holds for the restriction of omega bar, omega here. And so this constant will be no bigger than that one. And that concludes the proof. So to check if a function defined, for example, on the unit interval from the start can be modified to have a Holder alpha continuous version, we could restrict it to some countable dense subset and check whether that restriction is alpha Holder continuous. If it is, then we know from this theorem that restriction will have a unique extension to a alpha Holder continuous function on the whole space. It might not be equal to the original function, but we'll see that in the setup we'll give, it will be a version in the probabilistic sense that we need. So we need to work with a countable dense subset. Of course, the canonical choice would be the rational numbers, but in order to make things more computationally feasible, we're actually going to be working with a subset of the rational numbers, and that is the dyadic rational numbers, which we'll denote by this blackboard bold D. Dyadic rational numbers are precisely those real numbers whose binary expansion is finitely terminating. That is to say, for any, let's say, non-negative real number t, it can always be expanded as a binary expansion, some integer plus a binary sequence of zeros and ones afterward. And the dyadic rationals are exactly those numbers whose binary expansion here finitely terminates at some level. All of these BKs are zero after some finite stage. Now notice that if this sum terminates at level n, that means that we could take the common denominator 2 to the n here for all of these terms by multiplying all of the lower indexed BKs by appropriate powers 2 to the n minus k. And that means that we'll be able to express that dyadic rational number as an integer divided by 2 to the n. In other words, dyadic rationals can also be described as the union of all of these sets dn, where dn is the collection of all ratios, integer divided by 2 to the n. Now this is not a disjoint union, of course, just like the usual rational number ratio representation is not disjoint, but it's closer to disjoint than the usual case. We can characterize exactly when these guys overlap, and in fact, if we're careful, we can partition things in a way that will be very useful for us. If we fix any n, then we can represent any number t in the positive real line in this form here, which looks very similar to what we had for the binary expansion, except we've divided everything by an additional factor of 2 to the n. We just calculate them by doing the binary expansion of 2 to the n times t. And so we'll have the same result here. T is a non-negative dyadic rational if and only if in this expansion we get finite termination at some stage, although it will be earlier in this indexing than we had in the previous one. Now, one reason to partition things this way is that we really do have a partition. In particular, we find that our number t is in between a0 over 2 to the n and a0 plus 1 over 2 to the n, where a0 is some positive integer. And that corresponds to the nice partitioning of the whole positive real line into intervals of the form a over 2 to the n up to a plus 1 over 2 to the n. That is, we partition the positive real line into regular intervals of width 1 over 2 to the n. This is going to be very useful for us in order to have a partition of intervals of arbitrarily small fixed size. In particular, we can measure our Hölder continuity relative to each one of those granular intervals as a sequence of maximum meshes of our Hölder continuous path. Let's be clear about what I mean by that. Suppose we have a path omega that is gamma Hölder continuous for some gamma between 0 and 1. If the Euclidean distance between s and t is less than some tolerance epsilon, then what this will tell us is that the distance between the images omega s and omega t is less than or equal to s minus t to the gamma, which is therefore less than or equal to that constant depending on the path, times epsilon to the gamma. So in particular, if we take epsilon to be 1 over 2 to the n there, then that says that this is less than or equal to that constant times 2 to the minus gamma n. Now, putting that together with the partition that we stated on the last slide motivates the following definition. If I have some function defined on the dyadic rationals in the unit interval, taking values in some complete metric space, then for each n, we can define the maximum mesh of omega at level n, delta n of omega, which is just going to be the maximum distance between any two images of the path on times s and t, where s and t are chosen from dn, that is the dyadic rationals with 1 over 2 to the n as the common denominator, and such that s minus t is less than 2 to the minus n in width. And based on our various characterizations of dyadic rationals, this is really a maximum because this set here is the set of the form I over 2 to the n, where 0 is less than or equal to I is less than or equal to 2 to the n. That is the collection of all such times for s and t are sampled from here. And so this is a maximum over a set of size 2 to the n squared. And actually, it's a smaller size than that because in this set here, in order for this constraint to hold that s minus t is less than or equal to 2 to the minus n, we see that we must have, if s is equal to I over 2 to the n, t must be equal to I plus or minus 1 over 2 to the n. Now, let's make a simple observation here. By what we noted up here, if omega is a path in C gamma, then this maximum mesh will be less than or equal to the constant corresponding to omega times 2 to the minus gamma n for each n. And so what that means is that if we take an alpha less than gamma, then this strange looking sum here, the sum of all of those maximum meshes weighted by this exponentially increasing family, 2 to the n alpha, will be less than or equal to that constant k of omega times the sum of 2 to the n alpha times 2 to the minus n gamma. But because gamma is bigger than alpha, this is 2 to the minus gamma minus alpha n, gamma minus alpha is positive, and that means the terms in this series are exponentially decaying, which is to say that this will be a finite sum. Now, the reason that I did that silly little calculation is to note that this condition here actually also characterizes, even sharply at the boundary where gamma equals alpha, membership in C gamma. And here is the proposition, which is going to be our main workhorse for constructing continuous versions of stochastic processes. For any given parameter alpha in the open unit interval, define this constant here associated to each path. K alpha of omega is 2 to the 1 plus alpha, we'll see where that arises in the proof, times this sum that we have here, the sum of 2 to the alpha n times the mesh size delta n of omega. This is a sum that could well be, and most of the time is, infinite, but it's a sum of positive terms, so it makes sense anyway as a finite or infinite number. Now, if our path defined on the dyadic rationals in the unit interval is such that this constant here, this sum, is actually finite, then in fact that path is alpha Holder continuous. And moreover, this is an alpha Holder continuous constant for it. The proof of this is a little niggly, but pretty straightforward on the whole. Here's the core of the proof. If S and T are two distinct dyadic rationals in the unit interval, which means that there will be a unique n so that their difference is less than or equal to 2 to the minus n, but bigger than 2 to the minus n plus 1, then for that choice of n, the distance between the images of omega on S and T is less than or equal to this sum here, the sum from stage n up to infinity of the maximum meshes times 2. Now we're going to prove that in a moment, but first let's see why the proof of that gives us the proof of the whole proposition here. This sum here can be written multiplying and dividing by 2 to the minus alpha k inside. Well, inside this sum, 2 to the minus alpha k is certainly no bigger than 2 to the minus alpha n, since all those k's are bigger than or equal to n. And so that is less than or equal to 2 to the minus alpha n, which I'll write as 2 to the minus n to the power alpha, times the sum k going from n up to infinity of 2 to the alpha k, delta k of omega. And now here's the key point. This 2 to the minus n inside here, which I'll write as 2 to the minus n plus 1 times 2, well, that is, by construction, less than 2 times t minus s. And so, putting that over here, this whole thing is going to be less than or equal to, well, there's a 2 here, so there's a 2 to the alpha left over, times the sum, k going from n up to infinity, of 2 to the alpha k delta k omega, times this extra factor, t minus s to the alpha. Now we'll just throw caution to the wind and bound that by the whole series starting at k equals 0. And here we have the definition of k alpha of omega over 2. And that extra factor of 2 right there then gives us the full proof that this is less than or equal to k alpha of omega times t minus s to the alpha, as claimed. So to prove this proposition, it remains just to prove this claim. And to do so, we're going to use that n-width partition of the representations of the dyadic rational numbers. So fix two dyadic rational numbers, s and t, in the unit interval, and give their expansions at level n, as we discussed. That means that these terms ak and bk are all either 0 or 1 for every k, and they're both equal to 0 for all large k. Moreover, since t minus s is less than or equal to 2 to the minus n, as we noted, that must mean that the initial integer parts differ by at most 1. All right, the trick is going to be to truncate these two sequences. Let's just work with the S sequence for now. Let's define Sm to be this binary expansion truncated at level m. Of course, what we know then, since S is a dyadic rational, is that Sm is equal to S for all large enough m. Moreover, the difference between two terms in this sequence, Sm and Sm plus 1, is just the m plus first term in this sum here. So that's just equal to am plus 1 divided by 2 to the n plus m plus 1. And that am plus 1 is either 1 or 0, and so this is no bigger than the denominator there, 2 to the minus n plus m plus 1. Now what that tells us, by the definition of the maximum mesh, is that the distance between omega of Sm and omega of Sm plus 1 is no bigger than that maximum mesh delta n plus m plus 1 of omega. Okay, let's do that same thing for t as well. And so we have two sequences, Sm and Tm, which are the truncations of the binary expansions of S and T, but we actually know that they'll equal S and T when we truncate at a high enough level, let's say m bigger than or equal to n, chosen so that both of these will give equality for m bigger than or equal to n. Then by what we just constructed, if I look at the distance between images of successive terms in either of those sequences, that's going to be less than or equal to the mesh at height n plus m plus 1 of the path omega. From there, I can compute the following. I can estimate the distance from omega of the true number s to omega of its base approximation, this one here. And I'll do that by taking a telescoping series and comparing first omega of s naught to omega of s1, then omega of s1 to omega of s2, and so on down the line. Applying the triangle inequality to that, I get that that's going to be less than or equal to the sum, m going from 0 up to capital N minus 1, which is the point where we actually reach s, of the distance from omega of Sm up to omega of Sm plus 1. But we just established that those terms are less than or equal to delta n plus m plus 1 of omega. And now I'll throw caution to the wind and bound that further by taking the sum all the way up to infinity. And now I'll reindex the sum by calling this thing k, which means that the sum starts at k equals n plus 1. So this whole thing is less than or equal to the sum k going from n plus 1 up to infinity of delta k of omega. And the exact same calculations here, comparing omega of t naught to omega of t, will give us the same estimate. So if I combine those, then I can estimate the distance from omega of s to omega of t by first going from omega of s to omega of s naught, then from omega of s naught to omega of t naught, and then from omega of t naught to omega of t. The first term there we just showed was less than or equal to the sum k going from n plus 1 up to infinity of delta k, and the last term is similarly bounded by that same sum. And as for this term here, well, we established that b naught minus a naught is between 0 and 1, which tells us that t naught minus s naught, which is b naught minus a naught over 2 to the n, is less than or equal to 1 over 2 to the n, which therefore means that this distance, by definition, is less than or equal to delta n of omega. And so altogether we get that this is less than or equal to delta n of omega plus 2 times the sum k going from n plus 1 up to infinity of delta k of omega. But I may as well bound that with an additional 2 there, and that gives us exactly 2 times the sum k going from n up to infinity of delta k of omega, which concludes the proof of the claim, and therefore the proof of this proposition. Now that might all seem extremely technical, but it really is a very get your hands dirty computational way to check whether a certain function is alpha Holder continuous. And we're going to use it to great effect in the next lecture to prove the Kolmogorov continuity criteria for stochastic processes.